where a longer broadhead truly is going to make a difference, let's look at the normal force acting to the edge of the broadhead. So as the broadhead penetrates animal tissue, you've got, of course, the force acting this direction. This is the impact force. We can recognize that that's probably some function of velocity, and it's moving this way. And if we look along the length of the broadhead, we want to think about the normal force. The normal force is essentially the force between the edge of the broadhead and the material as it's cutting through. And so that force is going to be this direction. And the equal and opposite force is going to be this direction. So we would call this the normal force to this plane, and this would be, well, we're going to see that this is actually a component of this velocity. So the way we set this problem up is by identifying an x and y axis. So I'm going to call this my y-axis, I'm going to call this my x-axis, and I'm going to take this force vector and redraw it here and break it into its y and x components. So the way that we do that is by making a right triangle. So in the x direction, that's parallel to this line here, I'm going this way. That would be the x component of this force. And then the y direction would be going this way. And that would be the y component of this force. Okay, so what we're looking at now is this angle, which is the same as this angle. These two are the same angle. And this is the angle of the broadhead. So starting from the width of the broadhead and working along the edge back to the point. This is the angle. It's technically half of the included angle for the shape of the broadhead. I've got two examples, a 3-to-1 broadhead. This angle is a little bit less than 10 degrees, 9.59 degrees. For the iron wheel Y, this is just something I measured really quickly. I don't have this number from the website. I didn't see it, but I did measure it from some pictures of the iron wheel Y. It's 24.9 degrees. So this component here, which is the component of the force acting directly into the edge, it's this y component acting directly into the edge. We can get that very quickly from some very simple calculus, from very simple trigonometry, that f sub y is just going to be, well, if this is the magnitude of the force in this direction, then what we would just have is fv times, this is the sine of this angle theta. Okay, so work through this yourself. The sine of the angle theta is going to be equal to the opposite fy over the hypotenuse f of v. We multiply both sides through by f of v to get to fy is equal to f of v times the sine of theta. So what we're going to do is just plug these numbers in for these two different broadheads. So let's start with a 3-to-1 broadhead. F of y is f of v, whatever our impact force is, whatever this force is. We don't care about that. What we care about is the sine of theta term, because that tells us what percentage of the impact force is directly acting against the edge in trying to roll the edge or chip it or push it or anything else. And so that's going to be sine of 9.59 degrees. And if you plug that into your calculator, what you'll get is that you take the impact force and multiply it by 0.167. So basically, 17% of the total impact force is acting directly against the edge and dulling the edge, rolling the edge, doing whatever it's doing. And that's for a 3-to-1 broadhead. So this is the 3-to-1 case. Now let's look at the shorter, stubbier iron will as just an example. So Fy is equal to Fv. Now this time times the sine of 24.9 degrees. All right, you punch that into your calculator, and that would be the force here times 0.42. So this one basically reduces the force acting directly against the edge to 17% of the total force acting on the broadhead, on the arrow. This one, the shorter stubby or iron will, reduces that to only 42% of the total force value. So, in other words, for the iron will, the edge experiences significantly more forces acting on it as it penetrates an animal than the edge does for a 3-to-1 broadhead. This sort of supports my idea that the shorter, stubbier broadhead is going to need better metal to resist this stronger force acting directly on the edge, trying to roll the edge, dull it, chip it. And the 3-to-1 broadhead is going to get away with a lot less force acting on each portion of the edge. In addition to that, the 3-to-1 edge is much longer, so you have this force acting on a much longer edge. There's just a lot less damage done to that than there is to a shorter, stubbier broadhead. But as in the case of the iron will, if you use a tool steel or some other kind of really good steel that has extremely good edge retention, then this doesn't matter so much, because the whole purpose of using this broadhead is that the edge is going to hold up to these forces and will remain sharp as the broadhead passes through the animal.